Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to cover the concept of shear force diagrams and bending moment diagrams using one of two methods that we learned. So as you guys know, there's basically two methods to find a shear force diagram and a bending moment diagram. The first, which will be this example, is the more complicated of the two, and involves cutting the beam and then solving for the internal forces. So as you guys remember in a truss, we'd cut a bunch of the truss members and replace the members that we cut with a single axial force. Now we do the exact same things for beams, except, as you guys know, we have three forces. We have a shear force, an axial force, and a bending moment. And in last week's videos, as you guys learned, we were able to solve for those values at single points. But now we're going to learn how to do it for every single point across the segment. So it's a little bit more tricky. However, don't be discouraged, don't be worried, because in the next couple of videos, I'll teach you guys kind of a simplified method to determine these forces using a bunch of relationships that we use. And actually what we're learning today is kind of the basis of those relationships. So today's kind of like the proof video that will lead to nice relationships that we'll use in the later videos to solve these really, really quickly. Now, when it comes to the final exam, from what I remember, I've never seen them ask a specific method. And this method, it doesn't really have a name. I just call it the equation method because we have to cut the beams and form equations. Now, again, I haven't really seen this used on a final exam. Not to say that they will never use it. They could definitely use it, but I've rarely seen this. So I don't recommend, if they don't ask for a specific method, I don't recommend using this method. This method is time consuming because it involves cutting the beam. And every time you cut a beam, as you guys know, that's a free body diagram. And no one wants to do free body diagrams. Those really suck. In addition to that, you have to do a bunch of summation of forces, stuff like that. So one little mistake could lead everything wrong. And as we're going left to right on a beam, if you mess up somewhere at the beginning, everything else will unfortunately be wrong. So that's my little heads up with this. If you guys are just wanting the shear force diagram and the bending moment diagram nice and quick, I recommend the next three videos, as it'll teach you how to solve those for any situation you'll see in this course rather quickly. However, this is kind of the bare bones of it all, and kind of the more, I don't know. The first word that comes to my mind is classy, but classy is not the word I'm looking for. This is the more professional way of solving them, I guess, not the quick and easy way that the students always love. So as you guys will see, this is kind of a pain in the butt, but we'll get through it, and you guys will see, hopefully be able to see how we can solve for the shear force diagram and bending moment diagram with cutting the beam and determining equations. So with that being said, let's begin. Alrighty, so looking at this example, what it would like us to do is draw the shear and moment diagrams for the beam. So again, as I said, when it comes to drawing shear and bending moment diagrams, the question is always going to be the same. It's just going to ask for the shear and bending moment diagrams. But there's some little secrets hidden in this question. It's actually kind of deceiving. So even though it just says it wants the diagrams, drawing the simple lines will not be enough. Professors always look for two things. One is, are your lines the right lines? Are they linear? Are they quadratic? Stuff like that. But they also look for the values of these lines. And that's very simple, because if something's constant, you'll know the value at which it's constant. But what professors love to check for is maximum and minimum values of bending moment and of shear. So make sure that if you ever have a peak in your diagram, you have the value labeled next to it or on the axis, something like that. You will lose marks if you don't have it. But we'll kind of discuss that later on, because that will happen in this scenario. But for now, let's just jump into this scenario. So we have a beam. Again, it was in imperial units, but I just switched it to metric to make it nice and easy. Oh, actually I didn't switch it enough. So we got to change this to kilonewton times meters. And in these questions, as you guys will see, the first step is always going to be the same. It was the same as trusses. It was the same last week in internal forces at a point. And it's going to be the same this week and even next week into friction. And that is the first thing we're going to always have to do, is draw the free body diagram of the beam and determine the support reactions. So first thing I'm going to do, I'm going to draw myself a beam like so. And that did not work. All right, we'll try round two. So we'll have a beam. Wow, this is not working. All right, round three. This is the lucky round. All right, close enough. I'll take it. Or else we'll be here all night. All right, so here's my beam. I'm going to switch to red for the loads. So we know that A is a pin, so it's going to provide a horizontal and a vertical reaction. So I'm just going to go down like this. And I'm going to have my horizontal reaction as so. We see on more towards the right side of the beam, we have a reaction force, which is a roller. So we're going to have just a single force. I'm going to label these real quick. We got BY, we'll say AY, as well as AX. And as we see, we have a nice distributed load that goes something like this. It's linear. So that's the one thing I'm going to touch on real quick. This is a linear distributed load. So it's a y equals mx plus b sort of load. And this is one thing that has been confirmed, is that this will be the worst kind of load you will see. You will never see a quadratic or any order above distributed load. So linear distributed load, that's the worst thing that you guys are going to see. And this one is 30 kilonewtons per meter at the peak. And then one thing that's kind of sneaky is there's actually a concentrated moment at the end of the beam. And you can't really see it, but it's there to sneak up on you and mess up your grade. So this is 180 kilonewtons per meter. So before I end, I'm just going to draw some dimensions. Dimensions are always very, very important in these free body diagrams. Please do not forget them. So as we see, we got a 9-meter segment and a 4.5 meter segment. So 9 meters and then 4.5 meters. And then we know the distributed load, well, there's actually going to be a kind of a concentrated force that we use to represent this distributed load. And it's going to act right here. And for convenience, I'm just going to label it right now as F1. So far, all we've done is we did our free body diagram. Not very special, but again, these are worth a lot of marks in exams. So please make sure that you guys are always drawing your free body diagrams. So if I come down here, we can start to solve for things. So the first thing I'm going to do is I'm just going to find out F1 real quick. We're going to need it for AX, AY, and BY. Well, as you'll see, not really AX, but we don't need anything for AX, but bear with me. So again, to find F1, we're just going to take the area of the distributed load. And since it's a triangle, we know it's going to be 1/2 times the base. The base is 9, and then times the height, which is 30. So you throw all this into your calculator, you're going to get 135. And since it's a force, it's going to have units of kilonewtons. All right, perfect. So that's not bad. Now we can use equilibrium to start to solve for the rest of our support conditions. So if we do sum of the forces in the x is equal to 0, what we find is AX, well, that's equal to 0 because there's no horizontal forces on this beam, so we don't need any horizontal reactions. And again, even though this could change, it's very likely that AX is typically 0 because if you look at these questions, all we ever want to do is find the shear and moment. We're not really concerned about the normal force because those are very rare in beams. Again, beams are used for gravity loads, so vertical loads. Very rare do we have an axial load on a beam unless we're pre-stressing or something like that, but that's way beyond the scope of the course, so we're not even going to get into that. All right, so now we know AX is 0, so all we have left is BY and AY. So let's start with BY. Why not? So to do that, we need to take the sum of the moments somewhere about the point, because if we do sum of the forces in Y, we're going to have two unknowns, and that's not going to get us anywhere. So if we do sum of the moments, we can take it at A or B, but I'm just going to take it at A because my preference is always just to take the sum of the moments about the pin. And what I get when I do this equation, so I'll just expand it out over here, we see that F1 is going to create a moment about A, so we're going to have 135. And we know that this one acts at a distance of 6 meters, so 2/3 times the 9 meters. And if we look at this moment, it's going to create a clockwise moment, so therefore this is going to be negative. And finally, we got BY, so plus BY, which acts at a distance of 9 meters, and it has a counterclockwise moment, so that's why I put the plus. Excuse me. And then one thing that'll really start to trick students is we have to keep in mind that there's a concentrated moment at the end of the beam. And that concentrated moment is 180 kilonewton meters. So if you guys forget to put this in here, your moment's going to be wrong. Or sorry, your moment will be wrong, so BY will be wrong. And if BY is wrong, then AY is going to be wrong. And then all of your equations after that will be wrong. So that little moment right there, which I'm going to highlight just to show you guys, this little 180, as simple and innocent as it may sound, it's actually quite a killer in exams because a lot of people forget about concentrated moments. They always remember forces for some reason, but concentrated moments tend to scare them a little bit, but please don't forget it. So if we look at this moment, it has a clockwise rotation, so it's going to be a negative moment. So we're going to go minus 180. And all this is equal to 0. So only unknown in this equation is by. When we solve, we can say that by is going to be equal to 110 kilonewtons. And then it's positive, so it means my assumed direction of up is correct, so I'm just going to leave it as up. And finally, we can easily solve for AY now that we know BY by taking the sum of the forces in X is equal to 0. So if we do that, what we find is that we got AY coming up, or assumed up, plus 110, and this 110 is just BY, and then minus F1, which is 135. All this is equal to 0, and what we can conclude is therefore AY is going to be equal to 25 kilonewtons, also upwards. So at this point, we know all of our support reactions. Now we can go in and try and find the bending and shear moment diagrams. Well, shear and bending moment diagrams. I always get that mixed up. You guys have seen it in all the videos so far, and I'm pretty sure I'm going to mess up a couple more times today. But now we're going to get into the new stuff. So remember, up until this point, we learned how to find those internal forces at a single point. So for instance, let's say I wanted it at this purple point here. I know I can cut the beam there. I can find the value of my distributed load up here, and then I can solve for the forces at those points. Nice and easy. However, when we're doing these diagrams or these equations, we need an equation that tells us the shear at every point throughout a certain segment. So now the question becomes, what are segments and why do I need them? And if you guys remember, these forces, which I'm going to highlight right here, these ones play a big role in our diagrams. And the reason why is because they cause a discontinuity, they cause a jump. So unfortunately for us, there is not a single equation that governs the shear for this whole beam. What we're going to have to do is we're going to have to find a number of equations for each segment. And what a segment is, it's a part of the free body diagram. It's a part of the free body diagram where the forces don't really change. For instance, if I wanted to analyze this segment right here, as well as this segment right here. So I made two cuts of this beam and analyzed the left side of both of these cuts. As you guys will see, nothing will change in the free body diagram. I'm going to have a distributed load coming up, and it's going to end at some unknown point, but there's no concentrated forces in here to change things. However, if I keep the one on the left and I analyze that, and I analyze this segment over on the right side, the free body diagrams are going to be different for a number of reasons. One, my distributed load stops. So that one no longer increases. And two, I got a concentrated load of BY down at the bottom. So I'm going to have to account for that as well. So in this particular scenario, there's actually two segments we're going to have to analyze. Number one, which I'll draw in purple, is going to be in the middle of the distributed load. So I'm going to call this one segment 1. And then the second one, which we'll do in, let's say, pink, is after the free body diagram ends. I'm going to call this one segment 2. Okay, well now that we know that we have different segments, how do we solve for them? Well, the trick is we're going to cut the beam just like we would if we were solving for the internal forces at the point that we would used to. So we come down here and I say, okay, we got segment 1. So all I'm going to do is I'm just going to redraw the free body diagram as if I cut at segment 1, as if I cut on that line. So if I come over here, what I'm going to have is I'm going to have part of the beam, so not the whole beam. I'll make it a little bit longer just to make it easier for you guys to see what I'm doing. All right, and we'll come down a bit. So this should be good. What I'm going to do is, just like before with the cuts, I want to put all my loads in that segment on. So AX is 0, but we know that AY is not 0, so I'm going to put AY at the end. But instead of just putting AY, I'm going to put it in its actual value, which is 25 kilonewtons. I know I have a distributed load coming up like this, but we don't know what the distributed load is at that point. So I'm not going to put that point in there at all. And then as for internal forces, because we cut the beam, we have to replace our cut with 3 internal forces. So the first one's going to be shear going downwards. Again, this will always go downwards. We have a moment. In this case, it'll be counterclockwise. And then we have an internal axial force, which will be pointing away from the beam. So this is what we would do before. Oh, I guess then this would be labeled N. So this is what we would typically do before. And we'd solve for M, N, and V for that single point. And the thing that we knew about the point which made our lives easy is we knew the distance of the point, this distance down here. And I was just making sure that line wasn't crooked. We're good to go. So we knew this distance. And with that distance, we were able to solve for the unknown distributed load at the top, as well as determine our moment arm, stuff like that. But now we don't know the distance. And what we do for diagrams, so not for just single points, but for diagrams, all we're going to do is we're going to say that this distance right here is x. Because it could be anywhere along this first segment. So it could be, and I'll switch to a nice bright pink color so you guys can see. It could be right here. It could be right here, right here, right here, right here, right here, anywhere along that segment. So I'm going to erase this real quick, or else this will cause confusion later on. So since we replace this with x, and it could be anywhere along the segment, we have to keep in mind that our shear, moment, and our normal force will now be functions of x, because they could be changing without the segment. So what I'm going to do is I'm going to go m1, x, v1, x, and n1 of x. And the reason why I put 1 there is because it's segment 1. So again, if we have more than one segment, we're going to have more than one equation. So this is just to help distinguish the equations from getting confused. But now we need something else, and that's what is our distributed load as a function of x. So we need this w, I'm going to put w1 of x, and we don't know that. But in order to solve for this free body diagram, of course, we're going to need to know that. So let's use similar triangles to figure out what w1 of x is. So if we go up to the original triangle, it goes up to a value of 30 kilonewton meters over a distance of 9. So I'm going to come down here. I'm going to go, we got 30 kilonewton meters over a distance of 9. And I'm just going to label this a similar triangle so you guys know what I'm doing. And we know that since this has the same slope, it'll be equal to this triangle right here. and this triangle goes up to a value of w1x at a distance of x meters. So therefore, we know that w1 of x is equal to 30 over 9 x. And the best way to test this is if we look up at our original triangle, we know that at x is equal to 9, so at this point over here, we should get a value of 30. So if we come down here and go w1 at 9, well, we know that's going to be equal to 30 over 9 multiplied by 9, which gives us 30. It's exactly what we want. We know our equation for w1x is correct. Oh, excuse me. Throat's a little bit dry lately. All right. So the reason why we need w1x is because we know that this distributed load actually acts at a point. So this is just like F1 before, but since it's not exactly F1, we're going to call this one F2. And since we now know what W is, as well as the length of the triangle, we can find out what F1 is. So I'm going to come, or sorry, F2. So we know that F2, well, that's going to be the area. So we know that since it's a triangle, we're going to have 1/2. The base, well, the base in this case is actually x. And then the height right now is 30 over 9x. So we're going to have 30 over 9x. So we can simplify this, and what we get is we get 30 over 18 x squared. So now you guys can kind of see how the equations are being formed. Where are we getting these variables from? So remember, as the shear changes as a function of x, well, a lot of students ask me, okay, well, how does x even get into the equation? And this is how. It's this bottom x right here. Because of that, it changes the base of our triangle, which we have to put as x, as well as it changes this w1x right at the top. So when we put in w1x, which is 30 over 9x, we already get x squared. So we know that the shear throughout this segment is already going to be quadratic, which is kind of a nightmare for you guys. It's the worst case scenario you guys can have. But now, since we know F2, we can look and we can say, okay, I know F2, I know the 25 kilonewtons, I can start solving for V, N, and M. However, the question here at the top only asks us for shear and moment. So there's really no sense in solving for N because the question doesn't ask for it. And the oldest trick in the book is if the question doesn't ask for it, why solve for it? So what I'm going to do is I'm just going to skip N and we're going to go right to V. So if we do sum of the forces in Y equals 0, so just like before, just using simple equilibrium, we just look for all the forces in Y. So on the left side, we got 25 kilonewtons going up. So we're going to have 25, and that's going up. We got F2 coming down, and we know that F2 is equal to 30 over 18 x squared. And finally, at the end of the beam, we got a shear force also going downwards. So we're going to go minus V1 of x. And since it's in equilibrium, everything must be equal to 0. And if we look, we can solve for V1 of x using this. And we go V1 of x is going to be equal to, and for this, it's very simple. We're just going to move V1 to the other side, so everything else will stay the same. It's going to be equal to negative 30 over 18 x squared plus 25. So this is V1 of x, and this is for the first segment of the beam. So this is throughout the whole distributed load. Anything after the distributed load is not represented by this equation. We're going to have to find a different equation to represent what happens after. But we're going to focus on segment 1 here because we now need to solve for the moment, M. Let's come down here. I'm going to go sum of the moments. And then this is what confuses a lot of students. So again, where do I take the moment? Because I can take it anywhere. Well, what I highly recommend for these scenarios, always take the moment where you cut the beam. So I'm going to come down here. I'm going to say sum of the moment at the cut is equal to 0. So from this right here, we come up, we see that there's 25 kilonewtons. It acts at a distance of x meters, and this creates a clockwise moment, so it'll be negative. So we're going to go negative, and the value is 25 kilonewtons at a distance of x meters. Coming up here, we also see that F2 creates a moment, and it's going to be counterclockwise. So we're going to go plus, and then whatever F2 is, which we know is 30 over 18 x squared. But now we also need its distance. So in this case, we're looking for, and I'll go put this in green, we're looking for this distance right here, which we know is 1/3 of x. So I'm going to come down here, I'm going to put this distance as x over 3. And finally, if we look up, well, we're taking the moment at the cut, so V and N don't create a moment. However, the concentrated M1 will still be there, the concentrated moment. So that is going counterclockwise, so it's going to be positive. So we're going to have plus M1 of x is equal to 0. So this is another easy thing where we can just solve for M1 of x. And what we find is that M1 of x is going to be equal to negative 30. And at the bottom, we're going to have 18 multiplied by 3, so over 54. And then x squared times x is going to be x cubed. And then at the end, we got a plus 25x. It's plus because we have to move it to the other side. And plus 25x. So now we have an equation for M1 of x. So this right here gives us the shear and the moment for the first segment of the beam. So remember this first segment here, and maybe I'll label this segment. So the first segment, I'll highlight in purple, is this. So we now have an equation for all of this right here. This part of the beam is good to go. However, now we have to ask ourselves, okay, what about this segment of the beam, that second segment? Well, how do we do that? We cut the beam and create another free body diagram and solve for the equations using equilibrium. So it's very, very boring, but that's exactly what we do. So now we're going to move on. We're going to go segment 2. So first thing we're going to have to do, we're going to have to draw another free body diagram. So this is why this method is much more tedious than using relationships, because you're going to have to draw a lot of free body diagrams, and they take a lot of time sometimes. It's just kind of very boring, very time consuming, not a lot of fun. So in segment 2, we're going to have to draw everything on the left, so we know that we still have AY, which is 25 kilonewtons. We also have a BY now, because this is included, and this one's 110 kilonewtons. We have a distributed load, that doesn't change, but now the whole distributed load is in the segment, which is great, because for this force here, it's not F3, we don't have to solve for it again, this is still F1, which we know is 135 kilonewtons. And then the final thing is the internal forces. So since we cut the beam, we have to remember that there's going to be internal forces in the beam. So we're going to come over here, and we got N2 of X. We have our nice bending moment, which is going to be M2 of X. And finally, we have some shear, and we know that the shear acts downwards. If you guys don't remember why the shear acts downwards, please look at the videos from last week. They explain it in a lot of detail. Well, at least hopefully they do. So V2 of X. So now the question becomes this. And both actually work. So there's only going to be one trick. So we know that the length of this beam is going to be one of two things. I'm just going to put tick marks here. And the first one is I just say the whole thing is X. Now, this is not how I used to do it. I'll show you how I used to do it, but this is what I recommend now. And I'll tell you why. It's because it keeps the left side of the beam at X equals 0. In our equation, the very left side of the beam will be X equals 0. And then right here will be X equals 9. Now, this is how I recommend doing it. It's what I've switched to. Now, the way I used to do it, and it still works, is I can just keep X as this little part right here, and I can switch this to 9. But the one thing that I remember is when you get your equation now, and you're subbing in values, this point is now X equals 0. So your axis will shift a little bit, or your starting point. So what I recommend, I think it's the easiest, I just like to put that the whole thing is equal to 9, and then I also put in this, equal to X, and this little distance now is equal to 9. All right, so with this, our free body diagram is complete. We can go around and start solving everything that we need to know. So I don't even need to switch colors, because we're going right into equilibrium now. So I go sum of the forces, and y is equal to 0. Well, it's actually going to be really funny, because we're going to get 25 going upwards from the 25 kilonewtons, minus 135, plus 110, and then we go minus V2 of X, and that's equal to 0. So what you guys find, which is really kind of silly, or I guess silly may not be the word, but kind of interesting, is you say that V2 of X is equal to 0. So that's kind of funny how it just goes away to 0, but that's cool, I guess. Nothing wrong with that. I guess on an exam it would probably frighten a lot of students getting 0 as an answer. It could be some scare tactics or something like that. Excuse me. All right, so now we go with sum. Oop, I gotta change the pen color. So now we can go sum of the moments around the cut. So again, I always like to take where the cut is equal to 0. Now things are going to be a little bit messy. And this is another reason why I don't like this equation method where you cut it, is because things are going to get a lot messy when you take moments, because you need the forces, which could be in terms of X. But then you also need distances, which could also be in terms of X, and even worse. And in this case, it's even worse. And you guys will see why right now. So the first thing I like to do, go from the left and work my way right. So if we're taking the moment about the cut, we see that the 25 kilonewton is going to create a clockwise moment. So we're going to have negative 25, and this one acts at a distance of x. So that one wasn't too bad, but now it's going to start getting messy, because now if we look at the 135, it's going to be a counterclockwise moment. So we're going to have plus 135, and now we got to figure out the distance at which it acts. So right now it acts at this distance right here, and we got to ask ourselves, what is that distance? Well, we know that the distance from the left side to the force right here is 6 meters. So what does that mean? Well, it means that the distance that 135 acts is going to be x minus 6. So now you guys can see why this is going to start getting really, really messy. Come up here, same thing with the 110. It's going to create a negative moment, so we're going to negative 110, but its distance right now is going to be x minus 9. So again, to show you guys, I'll go dark green. We're looking for this distance here. So now we know that the complete distance is x, and then the smaller distance is 9. We can subtract them to get the distance, which x minus 9. Really messy. And finally, at the end of the beam, we got plus m2 of x equal to 0. So we can solve for this and have a single equation in terms of x and a constant. But as you guys will see, when you simplify this, you're going to get that m2 of x is equal to negative 180 kilonewton meters. So I'm going to just go here, and actually I'm going to change this because it equals 180, which is kind of funny, but this isn't really how you express equations, and I'm going to express them in pink. So it's just equal to negative 180, and what we usually do is put on the side in brackets that the units of the equation are kilonewton meters. This one's going to be in kilonewtons. This one will be in kilonewton meters. And this one will be in terms of kilonewtons. So now we have our 4 equations, 2 for each segment. So from here, it's just about graphing all these and then throwing them onto a piece of paper. And I'm not going to cover that because you guys are experts at graphing. But there's one thing I want to cover right now, and that's the moment diagram. So if we graph segment 1, so I'm just going to do a crappy little graph of segment 1. Excuse me. I'm going to show you guys exactly what I'm talking about. So this is segment 1. So right here, this is going to be x equals 9. And this will be 0 over here. And what you're going to do is you're going to get kind of a funny graph that looks something like this. Well, not that funny. It's going to look something like this. And this endpoint will be negative 180. But one of the things that the professors will ask you to do 100% of the time, they're going to say, what is the maximum value? They will always ask you what that maximum value is. And if you have these equations, it's actually really simple to find. So how do I find this maximum value? Well, I have an equation for m. So if I know the distance from the axis, so I'm going to go this light green. If I know this distance x right here, and that is probably a terrible color. I should do a whole video on that color just to mess with you guys. If I know that distance x, all I have to do is sub it into my nice formula. I'll get my maximum moment. But how do I find that distance x? So how you find that? M max, you put v of x is equal to 0. As you guys will see later on when we start talking about relationships, is the moment is actually the integral of shear. So how do you find a maximum? Well, you take a derivative. So the derivative of moment is shear. So if we set the v of x is equal to 0, we can find the value x where there's a maximum. So looking at my v1 of x, it's negative 30 over 18x squared. So v1 of x equal to negative 30 over 18 x squared, and then it's plus 25. And so what we want to do to find x is we're going to make this equal to 0. As you guys will see, when you solve it, you'll get a value for x, and that value is 64.5. Oops, sorry. That's the moment. Getting too far ahead of myself. You get 3.87 meters. So to find the maximum moment, and this will be covered more in detail using the relationships. I'm only kind of touching upon it now because I don't want you guys using this method. This is kind of my secret to you guys. I don't want you using this method. You guys just watch this half-an-hour video. You're thinking, okay, great, I'm a master at this. And then now I'm telling you, please don't use this method. And you're thinking, well, Clayton, you just wasted half an hour of my time. And sure, but why not? I can do what I want. So, this M max is going to be equal to the moment at 3.87. So we substitute that in and we get 64.5 kilonewton meters. So we can find M max, and again, I'll show you how to do this more in a better way, I guess, in later videos, but please don't use this method. That's kind of the moral of this video. Do not use this method. There are simpler ways. So if you guys are studying for the finals, please look at videos 9.2 to 9.4 for in terms of bending and shear moment. I told you guys I'd do that one more time. In terms of shear and bending moment diagrams, please look at those ones. It's much quicker. It's good to know this in case they somehow do ask you for an equation. Again, I haven't seen it done, but this year you guys never know. New professors, they like to try new things. We don't know what's coming. So know this method, but please focus on the other method. It's the best way possible. So that concludes this video, how to find equations. So thank you guys all so much for listening, even though I probably just wasted half an hour of your time. Please don't hate me too much. But yeah, no, thank you guys for listening, and I'll see you guys in the next video.